Okay, welcome to Chapter 9. So Chapter 9 is about parallel algorithms, page 267. And so unlike some of the other chapters in the book, this one has some really nice concrete examples. And so this one's not difficult to understand what's going on, and it's pretty straightforward. So just as an introduction, you know from real life that if you have more people working on a single task, it takes less time. I mean, right? There's lots and lots of examples of that. The bucket brigade. If you have to run to the creek and grab a bucket of water and run back and douse it onto the fire, that's going to be rather slow. But if you had a row of people that could pass the full bucket and pass the empty bucket, and it would go a lot faster, wouldn't it? So more people, right, make things go faster. That's not a difficult concept to do. I mean, that's essentially how the assembly line was put together, right? So how we manufacture cars is based upon people doing one little piece and passing it off. So we got 40 people working on a car rather than one person working on a car. So there's some terms here, and they're not difficult. A multitasking system. So a multitasking system is like a modern CPU, right? Come on. Where the same task could be divided up into multiple computers. And by the way, this was written before the term core really came out, so just use that in mind. Because a parallel system could mean two separate systems, two completely different computers that are combined together, or it could be just two different cores on the same CPU. So it's a little confusing, but let me go through it. So multitasking means a task can be divided among multiple CPUs, all doing the same thing, but with different data, right? That kind of makes sense, right? Like, I'm trying to do a sort, and so I break half of it out and give this to one CPU, and take the other half and give it to that CPU, and then when we're done, we combine them together, right? No big deal. Okay. A pipeline system's where I do one part and pass it on, and do another part and pass it on, do another part. Somewhat analogous to the assembly line analogy, right? Where I put the wheel on, the next person puts the interior seats in, the next person puts the windshield on, right? They're doing completely separate things, but each person does just the one thing. So the CPU just does one part and passes it on to perhaps another CPU. And then data flow systems is where I have one task and it fans out to like 5 or 6 processes that I do this part, but then at the end it has to come back together. So it fans out to a bunch of CPUs to work on, and then but there's only one answer, so I have to combine all the answers together. That's a very common thing, a pipeline, and these are not mutually exclusive. I mean, you could have a pipeline, you could have a data flow pipeline or a data flow, multitasking system. So most modern CPUs are multitasking. You have a single CPU sitting out there doing multiple things, all right? I mean, right this very second, it looks like my machine is idle, but believe me, it's not. It's out there doing something. Okay, so they made some categories on page 229. And so these have to do with, is it a single instruction or multiple instructions that are happening versus a single CPU / core and multiple CPUs / cores. And so the first one is the single instruction, single data, okay, which means just one CPU doing one thing and things are done in sequence. Now, if you only have one CPU, and I'm going to go ahead and say one core, you can still have what's called a multitasking system, but it's not really doing multiple things simultaneously. What it's doing is faking it out. It's in fact, in the old days, it was called timeshare, because like timeshare condos was kind of cool at the time, where if I have 3 things to do, I spend 1/3 of the time doing this, and then 1/3 of the time doing this, but the machine is so fast you never even notice that it's not actually simultaneously working on 3 things, okay? So a single instruction, single data does not have the ability to actually work on 2 things simultaneously. And believe it or not, most CPUs of just a few years ago were in that category. They faked out that multitasking thing by just doing things in sequence very rapidly, so it kind of sort of looked like you were multitasking, but you really weren't. Okay. The next one is single instruction, multiple data. I've got basically one CPU, but I'm working on different sets of data. Now this one's a little more harder to understand what we're talking about. But a classic example would be like a specialized thing like a vector processor, or something like, like in a graphics card where you have, lots and lots of cores to do processing. So I have one thing I'm trying to do, one CPU, and then I'm, a single instruction, one thing, but then I have multiple pieces of data that I'm working on. Okay, that one's kind of hard to visualize. Okay, multiple instruction single data means I'm doing multiple things, but just with one set of data. Okay, one set of data and I'm doing multiple things to it. And then, of course, the last one is multiple instruction, multiple data, which is pretty doggone common now. More than one CPU working on different tasks with different data, right? And so that's the way typically a typical system that we have today, an Intel desktop processor, it probably is a multiple instruction, kind of sort of single data most of the time. Most of the time, I have 4 cores on this machine right here that we're looking at. And one core is doing like 5 things, and this core is over here doing 4 things, and this core over here is doing 3 things, right? And so each one of the cores is getting a series of things to do that kind of look like they're multitasking. But rarely in that scenario do I have this core and that core working on the same data. Now, you can do that. It's not very common where you combine cores together. Now, there's some graphics processors that'll look at the number of cores that you have and go, whoa, it looks like you got 16 cores. I'll take 8 of them to run this game. Now, you might think that is incredibly prevalent. No, it's not. Most games today, the CPU is still single-threaded. Yeah, I know. Now, the graphics processor is multi-threaded like you never believe. But just the CPU part, it's not all that common. There are some specialized software that meets that multiple instruction, multiple data kind of a scenario. Okay, so a modern, 8-core Intel desktop processor is probably it could do multiple instruction, multiple data. How common is that? It's capable. Okay, if I ask you from an architecture perspective, which could it do? Well, multiple instruction, multiple data. How often is that? Not that. It's not very often. Okay, so let's go on. So architecture on page 270, they talk about behind the scenes. How do they do this? How is memory and processors physically connected and shared? So there's a term that they use that talks about loosely coupled. And so now when we talk about coupling, we're talking about between the CPU and the memory, okay? Not between CPUs, but between a CPU core, I can go ahead and say that, and a chunk of memory. Okay, so it's how physical memory is connected to the CPU. So in loosely coupled, each CPU has its own physical memory. Okay, now in modern terms, this is called NUMA, or non-uniform memory access, NUMA, and typically only found on servers. Now, once again, even here, we're talking about physical CPUs, not logical cores. Okay, so I go get me a super duper, Threadripper kind of a doodad, and I got 2 CPUs on my motherboard. This CPU has a bank of memory, and this CPU has a bank of memory. I might have 64 cores up here, but that's not what we're talking about. We're talking about one physical CPU and a bank of memory, one physical CPU and a bank of memory. Okay, how common is that on a desktop? No. In a typical desktop environment, there's one physical CPU and one physical bank of memory. That's it, okay, in a normal, typical kind of a scenario. So tightly coupled is the physical memory shared among all the CPUs, or in this case, cores. So, and by the way, we're not talking about like virtual memory space, because each core could have its own virtual memory. That's not, we're talking physical now, okay? Now, by the way, I find these terms to be slightly counterintuitive. When I think of loosely coupled, my mind goes to coupling between CPUs. That is not what they're talking about. And what they're talking about, loosely coupled, is between the CPU and the RAM. So tight means that tight means with other CPUs. Okay. All right. So, which of these two do you think represents a modern, Intel 8-core desktop processor? Is it going to be one of those that are tight? Is it going to be loosely coupled? Remember, I just said loosely was the one where you have more than one physical bank. Is that normal? If you crack open and look at your motherboard, are you going to see more than one bank of memory? No. Okay, so it's... All right. So the next one is, how the heck do they communicate? All right, so when we get to this part, we're really going to have to stop and talk about clustering. So, Raspberry Pi has been around for quite some time. By the way, this article is like 3 or 4 years old. So I want to build a Raspberry Pi cluster. So I have my own little motherboard, my own little CPUs. And so, what do you need? Well, I need, like, in this case, they're using 4. And I stick them together by using, this is the power cords, the USB power cords. These are the Ethernet, the network cables. And so these things are connected together with an Ethernet cable. Cool. And then you have to install some stuff and set up some network and set up some, encryption keys and install this thing called a message passing interface, which is the glue that says when I want to, do prime number factoring or something, I don't know. Then I send that task off to this side, and this is how each one of the nodes in the cluster talk to each other over this message passing interface. Okay, cool. And so you put it together, and how do I do this thing? So here's this thing with calculating prime numbers with Python. And so typically there's one thing is the controller, and then all the rest are the data guys. Okay, so in this case there's 4 physical Raspberry Pis, one of them being the controller that the human talks to. It uses MPI to talk to the other guys that actually do the work, the data ones. It does the data things and then sends the answers back and then spits them back out. So in this particular case, this is a classic example of a cluster, which kind of sort of sounds more like what they're talking about in the book. I mean, the example I've been using up to now has been, CPUs and cores, but you can kind of sort of tell they were kind of thinking this. Okay, having said that, how do you connect these guys together? So figure 9.1 on page 271 means every single one of the nodes in the cluster can talk to each other. That's exactly what that thing did in the Raspberry Pi example, right? Had Ethernet cable going to an Ethernet switch, right? Any one of the nodes can talk to any one of the other nodes. Okay. You could also have a ring or a mesh scenario like this where they can talk to the adjacent ones. But, if I wanted to go from 1 to 6, but I have to go through some stuff, that's a kind of a pain. And then, of course, a ring thing. And these aren't all that prevalent. I rarely think you'd ever find one of these in real life. It just doesn't make much sense to have it that way. Although, I will swear that this right here, this mesh network, kind of sort of sounds and looks an awful lot like those NUMA motherboards. I'm just saying, because if I want to share a piece of memory from one NUMA bank to another NUMA bank, it's a pain in the butt. I mean, you basically have to go, oh, hang on, let me set this thing up, and we'll copy from over here, and we'll copy it down to there. Kind of sort of looks like that. Kind of sort of. Okay, so one more time. Which of these network communication models do you think would represent what's going on inside modern desktop? I mean, can the cores talk to each other? Do they have a ring? Do they have a mesh? Can any core talk to any other core? Yeah. Okay, so on page 273, you talk about the principles of paralleling analysis. So there's 2 ideas that they come up with. One of them is the speed up, right? If I add more CPU cores, it's going to speed things up. And the other is the cost, because, right, if I do that, it's going to cost me more. Okay, we're coming up on the 15-minute mark, so you guys know how this works.